Next up, I want Porto to come on and talk about EIP-4844. And there's a lot of 4844 stuff going on here. Some of you may know how this helps us get to really, really cheap data and transactions. And there's a lot more that people don't talk about. And we're going to take about 44 minutes, maybe less, to cover all those specifics. So we'll get Porto to join us in a second as we get to load up the slides. And in the meantime, if you have any other questions that come up for Proto or Jesse or anybody else, please let us know and we'll be able to kind of relay those questions to you and to the speakers and get those answers. So without further ado, let's welcome Proto. And hi, how's it going?
It's going very well. Thank you for the introduction.
Absolutely.
Hello, everybody. I'm Protolambda. I work at OP Labs. I'm going to present about EIP-4844. Okay, so let's jump into this. 4844 is an EIP. It's about a year old now. It was started during ETH Denver. And, well, let me get started with the actual slides. This works. A moment. There we go. Right, technical issues. It's like a curse, starting with the presentation of Calvin. So, hello, I'm Proto. Work at OP Labs. Proto-Danksharding is kind of a meme. It's this name that's been attached to 4844. 4844, what it really is, it's the first iteration of the sharding roadmap of Ethereum. And this longer term vision is like inspired by the work by Dunkat and by Vitalik and others at the research team. However, we cannot wait. We want sharding on Ethereum today. Like, these are multi-year research processes. And so instead of trying to do everything at once, we, as engineers, we are looking to build this first iteration. And this is a collaboration between OP Labs, Coinbase, as well as all the different layer 1 client teams, and the research team, of course, of the foundation. That's putting together resources to implement the transaction pool changes, the blob storage, the syncing, everything that's involved in this first iteration of sharding. And so what I'm going to tell you about is really like, what is this thing? What is 4844? Why are we doing this? Like, how does this work on layer 1? How does this work on layer 2? And then I'll talk a little bit about the fee structure of 4844 and about the clients and the progress we've made so far. So what does EIP-4844 do? EIP-4844 increases the data availability for layer 2 to about 0.5 megabyte per layer 1 block. For context, the current data availability is around 70-ish kilobytes. And so this jump up in data availability increases the capacity that is there for rollups to post their data to. If you've watched the talk from Calvin about how these rollups work, then you're now familiar with the concept of a data availability layer. The data availability layer is kind of hijacked on top of the legacy Ethereum. We use call data, which is meant to be an input to the EVM. But instead of using this call data, what we intend to use is blob data. Blob data is like a specialized resource, so we can have more of this without putting a lot of more strain on these layer 1 nodes. And as you can see, rollup popularity has been rising. Like, around end 2020 is when the idea of a rollup-centric roadmap started to really take off, around the launch of the beacon chain. And since then, the rollups have taken more and more of the data of layer 1. So half of the current capacity, like half of the data inputs to the EVM, are not actually inputs to the EVM, they're rollup contents. And so we want to change this and optimize so we can have more of these contents. Because why? Well, 97% of the fees on layer 2 today are actually just paying for the call data on layer 1, and they're basically misusing this resource. This resource is not efficiently utilized to derive the layer 2 chain. Well, this is kind of what it looks like. So this is where transaction fees are going, and the thing we want to try and optimize. Like this total could be much, much smaller if we tackle the largest cost factor here. Like as a layer 2, we're not asking a lot of fees. It's primarily just data fees, and we'd rather have a lot more users that can adopt Ethereum through layer 2. And we can do so by utilizing shard data to host all the content. So this is what layer 1 looks like today. Merge is complete. Got to remove one slide leading up to this. In like the modular blockchain steps, we have a consensus layer and an execution layer now, but it's only the start of modular blockchain. What we are looking at today on Ethereum really is kind of this hack where we have layer 2 and it's attached to the call data of the EVM. There's no clean separation, and although we have these fault proofs and validity proofs to verify outputs of the EVM, we kind of have this strong coupling idea, or like how our wallet should be secured. It's not efficiently attached to layer 1. And so what we want to do with 4844 is to model it like this, where we have a consensus layer, we have an execution layer, and there's this layer 1 data, which technically speaking, it's part of the consensus layer. The consensus layer holds onto the data and votes on which data is available or not. And then through the execution layer, the data is registered and paid for. But this data is really meant to provide for these rollups for layer 2 to scale. And this is only the start. Like 4844 is an incremental step towards full sharding. What we're looking at after 4844 is full Danksharding, which basically means we can support a lot more of these data blobs. And how do we plan to support this? This can be supported with data availability sampling, which is this security technique for validators on the network to randomly poke others on the network to see if data is available. And the poking here, the sampling, can be dramatically improved using redundancy and using these efficient proofs over the data. And so I'll talk a little bit more about how these blobs are structured. They are structured in a very particular way where they are future compatible with this full sharding vision. Okay, so how does EIP-4844 really work? Now there is this new blob transaction type, and the blobs that are paid for, this content, the data, is held into the beacon node in the consensus layer for 2 weeks approximately. And what this means is that we separate this idea of syncing and this idea of security. Syncing, you should be able to fetch the layer 2 state from any place, just as with layer 1. The critical part really is this last 2 weeks of data. And so as intuition, you could think about a CDN or some service where it's much, much cheaper to provide, host, and like cache the data and distribute it if the data doesn't change versus changing data. And similarly, like this recent amount of data, it's more unstable. It's still being voted on, it's uncertain. The layer 1 might propose it, but not actually make it available to those that rely on it. And what we want to secure really is that any verifier of layer 2 is able to get the data and then able to use the data on top of this older state of layer 2 to get the very latest state, the tip of the chain. And then using the latest state, they can produce any, like with full data, they can produce any proof that they might need to counter any false claims on layer 1 or to produce a validity proof themselves on layer 1. And this is what secures the rollups. It's really this recent data that's important to make available. And then the older data we can optimize. And so this task of Ethereum changes to how can we make the data available to these layer 2 networks that rely on it to secure all their full assets, right? This is special data. It's not just that we can use regular storage services. It has to be available. And this availability, I'll talk more about this. It's just a strong feature of sharding where this type of resource that Ethereum was lacking is dramatically increasing. And then you ask, well, who's paying for this resource? How does this work? There's this new transaction type. And similar to how you can run the EVM, you can now also attach data to Ethereum to make it available. And what this means is that there's a regular EIP-4844 transaction. And the transaction contains some pointers. And these pointers, they point to these separated blobs. And the idea here is that the transaction registers the fee payment and is processed by the EVM, whereas the blobs, they are separated and they go into the consensus layer, into the beacon node. So here's the transaction in more detail. The nice thing about this transaction is that it's structured using the latest encoding format, SSE, that the beacon chain also uses. And then the functionality is mostly the same as with EIP-4844. It's just strictly a small extension to express the fee payments and to register the data. And so there's this max fee per data gas that's added, and there is a list of hashes that refer to the commitments that then refer to the full contents of the blob. And the pretty thing here is that the data hashes, they are easily embedded into the transaction. They don't take a lot of space. They are 32 bytes long, so they fit in the EVM very nicely. Whereas these commitments, these are 48 bytes. They go into the beacon chain, and they are KCG commitments. KCG is this special commitment type, similar to what a Merkle tree does, except instead of a Merkle proof, you have an opening to prove any particular point or multiple points in this set of blob data. And this allows you to build an efficient proof for the contents of the blob when you need it in the EVM, but otherwise basically optimizes away the proof data. And this is the key part for full Danksharding, for this full vision of data availability sampling, to have this type of commitment in there. And so what this really means is that the transaction goes into the EVM. Like at first it's generalized, it's abstracted as this message, just like any other transaction. The EVM doesn't really know about transaction types. But this additional wrapper data, the commitments and the blobs, they don't go into the EVM. They leave the execution layer and they go into the consensus layer. So how does this lifecycle work, right? I'm this layer 2 user. I want to utilize the shard data. What does this mean? Well, you just use Ethereum as you would use it today. It's a lot like just sending a layer 1 transaction, except it's on layer 2, it's on a rollup. And then the rollup operator, or the sequencer, they bundle the transactions. And then the transaction bundle, what really happens there is that needs to be submitted to layer 1 to make it available for verifiers to see and like reproduce the layer 2 state. And so this bundle of transactions, it's encoded. It might be split across multiple layer 1 transactions. But really the key here is that the data is encoded into blobs, and these blobs paid for with blob transactions go into the layer 1 transaction pool. And then the beacon chain proposers can pick up on transactions from the transaction pool. They can build their execution payload. And then along with the execution payload, there's now this new addition of a blob sidecar. This is additional data that comes with the beacon block. And there's a separate syncing method to distribute the sidecar. And the beacon chain distributes the data. And then everybody on the beacon chain, they hold onto it for a certain amount of time. So they hold onto it for like 2 weeks, maybe a month, depends on the exact parameters in EIP-4844. And then the execution payload stays in layer 1 with the fee payments, but then the blobs eventually get pruned from layer 1, meaning that the resource usage on layer 1 is bounded. Bounded resource usage is like this long-term goal of Ethereum, where we shouldn't always keep growing the state and growing the chain history. We want to make this sustainable. And so this is a really important feature of 424 and of sharding in general, that once you start adding a lot of shard data, that we don't rapidly increase the resource requirements of regular layer 1 nodes. And then it's for up to the layer 2 to persist data long term. And this is not at risk anymore after the proofs that secure the assets have already largely been completed. It's then up to the layer 2 community, the stakeholders of that rollup, that the now fully agreed upon layer 2 state is there for others to sync and join this layer 2 ecosystem, similar to what we do on layer 1. And so this is what it looks like in terms of the network. We have the sequencer and this transaction pool. You could think of it just this cloud of suggestions for the layer 1 proposer to build the perfect block. Then the blobs and execution payloads make their way into the beacon chain. And then the other nodes on the network, they verify the fee payments and they verify the data is there, but then the data is retrieved by another layer 2 node, the layer 2 verifier, to reproduce the layer 2 state, using this data as an input to the rollup. Again, parts to talk by Calvin to learn all about how the rollup processes this data. Now, how does this work between the layer 1 consensus layer and the layer 1 execution layer? We used to have this API called the engine API, and we have the same API right now, except we are adding one method and one type. We're adding this blobs bundle so that everything that comes with the transactions can be paid for by the transactions, but it's then bundled together and separated from the regular execution payload. And so the consensus layer can retrieve the execution payload to embed in the beacon block and can retrieve the bundle of blobs, the sidecar, to then distribute to other beacon nodes for the period that the data needs to be available. So we talked about like how 484 works on layer 1. And to complete the picture, we also need to talk about how EIP-4844 works on layer 2, because this data would be kind of useless if there were not all these many different rollups building ecosystems, extensions of Ethereum on top of this data. And so what it means to update layer 2, it means to update the proof so that the inputs that we now change about the layer 2 make their way through the layer 2 state transition to produce the new layer 2 output. This transition has to be proven on layer 1. And then we change the verifier code to actually pick up on this data, to process it in the first place. And we change the batch submitter to even submit the data before the verifier can pick up on it. So it's really batch submitter first, then verifier, and then the proof shows the full transition of processing blob data, running the layer 2 state transition, and then producing the output that then is claimed or validated on layer 1. So I'll show this simplified ZK validity proof. ZK rollups, they all work a little bit different, but if you generalize them a little bit, what it looks like is that there is some form of computation on layer 1 that verifies witness data to show one state route, one claim going to another claim, and the proof shows that this transition is valid. And so how this works is that we first want to prove that we have the correct data in our system. And since not every ZK rollup is built with KZG, what some will have to do is this proof of equivalence to show that the KZG commitment over the data is equivalent to the commitment that they prefer to use. Luckily, because this is a polynomial commitment, this can be done rather efficiently as part of the ZK proof in a way. And so there's this precompile that allows you to evaluate a polynomial, do a single point evaluation. And this can be used to do a random evaluation, and random in a way that you can securely verify it against another evaluation in another different kind of curve or some system that the ZK rollup prefers to use. And then once you have verified the inputs, you can run your regular ZK validity proof using the same form of inputs that the ZK rollup is already built for, and then produce the output, or verify the output really. And then all you need to do at the very end of this is to just persist the outcome. Now, we also have optimistic rollups, and they work differently. However, we use the same precompile. So the additions to the layer 1 EVM, when we want to verify blob data for optimistic rollups or for ZK rollups, they are the same. We can have this common utility to verify a single point of blob data, except that we use the precompile slightly differently, where like an optimistic rollup, they have the notion of this pre-image oracle, and the pre-image oracle is used to access any history in the layer 1, which could include blob data. And then depending if it's a regular hash or the special KZG commitment, we use a hash function to verify the pre-image matches the claimed hash, or we use the point evaluation precompile to verify a piece of blob data at a certain position matches the commitment to the set blob data. And this extended pre-image oracle, we can plug into the existing single-step verifier. So it doesn't matter if you're like an WASM proof system or a MIPS proof system or a RISC-V proof system. If you have this general idea about loading inputs through pre-image verification, you can plug in this new type of pre-image backed by blob data. So this is kind of what it looks like to integrate it into the verifier. So we talked about the proof part of layer 2. We also have to modify the verifier. And then the batch submitter is really just the reverse system of the verifier. In the talk of Calvin, you have seen that there's this input stream and there's output stream. Now this is the process that takes the input stream and converts it into the output stream. In the OP stack, it's called the layer 2 derivation pipeline. And what it really does, it traverses the layer 1 chain, the chain of inputs. It retrieves the data. It processes the data. It might use a layer 2 execution engine to process the data. It's really only the retrieval that we have to adapt to this new type of data. And then the batch emitter, which does the reverse process, then it takes a layer 2 block that has been sequenced. It is going from the layer 2 block. It extracts the inputs, encodes the inputs in a batch. And then the batch needs to be encoded in layer 1 transactions. And this layer 1 transaction is published now with Blob data rather than call data. Okay, so we talked about how layer 1 works, how layer 2 works. If you really want to slot them together, we need the layer 2 operator to pay for this resource of layer 1, this new type of resource. And what this requires is a new type of gas metering. Except that I wouldn't even call it metering at this point, because the EVM does all these complex computations, whereas data is just static. It's very easy to meter. We would look at the amount of data, we can translate it to the amount of data gas that's required to pay for the data. And now this data gas, it works very similar to regular gas, very similar to EIP-4844, where we burn the funds, we burn the fees, if there's an excess in usage. And then in the block header of the execution layer 1 block, we maintain a special variable that can track what kind of excess there is. In EIP-4844, we know this as the base fee. The base fee goes up if there's an excess. It goes down if there's not an excess. You could express this in many different ways. It doesn't have to be a floating point like variable that moves around. It could just be more discrete and say, you could say, oh, there's this much gas that's being utilized over the expected amount. And so what this looks like is that the more excess there is, the higher the price goes. And note the y-axis here, it's a logarithmic y-axis. And so exponentially, the cost goes up if there's more excess usage. And so it balances itself out. If the excess usage goes up, prices go up, and then either users are willing to continue to pay elevated prices to continue to use the target usage, or they compensate and they start using less for a little while, and then the prices go down again. And so the base fee in EIP-4844 or the excess data gas in EIP-4844 help balance out the resource utilization of the chain. So we target half, and we have a maximum capacity of twice the target, similar to EIP-4844, except now with data gas rather than EVM gas. This is how this is expressed in the EIP. It's a little bit hard to parse because the formula is different, but it has the same properties. So just at the same rate as EIP-4844, a rate of 1.125, and it goes up exponentially this way, or it goes down exponentially. This depends on the resource usage. And the limit is twice as much as the target. And the only addition that we need to maintain this state is this one field addition to the block header to track the success. Okay, things are going well so far. We've talked about how 4844 works, both in layer 1 and layer 2, how the fee structure works. But if you are interested in diving deeper into this to really understand it, you should look at the specifications. This is an EIP that spans across multiple layers of Ethereum. So there are consensus specs, and then there are execution specs. The consensus specs, they're scheduled per hard fork. They're isolated per hard fork. Whereas on the execution specs in our EIP system, they are targeting just specific features of EIPs. Now there is a new execution specs process that describes the EVM in Python. Expressing 404 there, I think, will take a little bit longer, but the specs are complete. The EIP describes the execution changes, and the consensus specs have all the consensus layer beacon chain changes. And then what would things be if there were not other specs repositories? So we talked about the state transition changes with consensus and execution, but there are also APIs that have to be extended. So there are the execution APIs to support a new transaction type. There's the engine API to pass along the blocks, the blobs between the engine and the beacon node. And then there's the beacon API, which has been modified to fetch the blob data. This is the API that layer 2 clients, verifiers, would now start to use to pull the blobs from the beacon node into their layer 2 node. And then they can cross-verify it against the data hashes that have been registered in the transactions that they already parse as part of the regular rollup traversal process. Now, implementing all these specs is not easy, but we're getting there. We have 5 different consensus layer teams and 5 different execution layer teams, actually more than this even, implementing the specifications and participating in testnets. So we started with just Prism and Gap as a prototype a year ago during ETH Denver. And since then, we have improved the syncing methods, improved the transaction pool, and we're still polishing various different things about the EIP. But the specs are stable, and so clients are moving forward. And now we have all clients participating on the same testnets. We have this client interoperability. And then it doesn't stop with just client modifications. Part of EIP-4844 requires this new KZG commitment to really be forward compatible with the long-term sharding vision. And this vision requires a trusted setup, or this KZG ceremony output. And this thing has been running for almost 2 months now, I believe. And also, there are about only 2 days left. So if you still want to participate, there's still a chance. This thing is hosted online, and you can use various different clients to participate. I'm showing you this server graph because it's kind of insane that so far we've had over 70,000 contributions. And when I was sharing about 44 just 2 weeks ago, I think we were at 50,000. This number is rapidly increasing. And the more contributions we have, the better, because the more we distribute this responsibility over not repeating all the inputs to the ceremony, and just one of the inputs has to stay private, hidden. It's like toxic waste to secure the final output. And then this final output is used to secure the blob data effectively. And there are various fun clients. There's not just the official clients. There are also meme clients. So there's this front end that is Dogecoin themed. I recommend just browsing around the KZG clients and to try and participate in fun new ways. And after this 2 months of regular participation is over, there's also a special time allocated for teams and participants to do special contributions, to mix in their randomness in different ways to create more diversity, to reduce the risk even further. But yes, 70,000 participants, it's kind of crazy. This is already 10 times, if not 100 times more than what most ceremonies are getting. Okay, let's talk about progress. So this EIP has been around for almost a year. And since last year in Denver, we've achieved a lot. We've worked on prototypes, we've worked on the EIP draft, then transformed into more specs. Then there were workshops, more education, DevNet started. This is something where I really appreciate the help of Coinbase contributors and like other early folks like Terrence from Prism, who like put a lot of time into these early prototypes to show that it works, to show the viability, to explore optimizations. But now we're at the point where we're running DevNets more regularly, and the KCG ceremony is almost coming to an end. And in DevCon, we started DevNet, or shortly after DevCon, we started DevNet 3. And then earlier this year at the Interop event, there was this DevNet that really pulled in all the clients, where like you can see that it's viable to ship in a hard fork. There's this interoperability problem with many EIP changes, where not all clients always implement the same thing. But clients are agreeing on the same Blob data. And with more testing, more polishing, we can ship this as part of a future layer 1 hard fork. And so currently this is scheduled for the DNAP hard fork, which is the one after the withdrawals. Right now we have various different testnets behind us. Started with version 0, the hackathon. Then there were various different devnets. And increasingly we have been extending this from prototypes to something that's like adopting all the spec changes and the latest features as discussed during this interop testing. And the latest features really, they are the transaction type, the transaction pool hardening, and the decoupling of blobs. And once these things are finished up, then we're looking at the final stretch, the final like milestone towards like a production ready for it for. And then hopefully can go live with the next hard fork after the withdrawals. So DevNet 5 is coming up. This updates the transaction type primarily. This is somewhat of a breaking change. The update here is that we want to perfect the way we structure SSC transactions and get it right. If this doesn't work out, we might revert to an RLP transaction, but right now there are strong proposals for SSC transactions to shape the way like we sign over transaction data in a more structured format, which will be very good for layer 2 long term to prove any data about any transaction. And then we have some network optimization, decoupling of blobs. Like what this really means is that the blobs and the beacon blocks are gossiped separately. And so the smaller the messages, the more effective gossip sub is at propagating the data efficiently and without duplication. So this also saves us more bandwidth. And then we have transaction pool hardening, meaning that we don't want blobs to have a negative influence on the regular EVM transaction pool. So we're trying to isolate the properties of these blob transactions as much as possible, have a really strong implementation that can handle the data. And so this likely will be like a pool-only mechanism where we avoid putting in large amount of data if we already have the data. And then there's more testing. There's always more testing. If you want to contribute, this is probably the best place to contribute. We are building more test vectors. There's work on Hive, and there are various other things to benchmark 404 to make sure it will run well on layer 1. So if this is still not enough for you, look at EIP-4844.com. We have a question and answer section with Vitalik answering things about 4844. There are various different resources you could read more about 44. And then if you want to get into contact, if you want to really contribute actively to the implementation, to like analysis of the KCG ceremony, or like other post-processing, or perhaps you just want to visualize the blob data, or maybe you want to contribute to the new block explorer that visualizes blobs. There are all these tooling efforts as well. It's not exclusively client development. During DevCon, there was a team building a block explorer, like an experimental block explorer specifically for this data. And during the EVE Online Hackathon, I also hope that more teams can build cool and new interesting tools that utilize this new concept of blob data. So yes, any questions? If there's time left, we can go through some things. Otherwise, let's scale Ethereum together. I'm looking forward to everything that's being built during this hackathon. Thank you.
Amazing. Thanks, Proto. There's a lot of time left for questions, but you were surprisingly on a 44-minute mark. So but just verify this again after we shot this video, but this was actually very informative. And I think this is the only resource now that exists on the full depth of what 4844 is. So thank you so much. And this has been awesome.
Yes, my pleasure. Thank you for hosting this.
Absolutely. Take care.